Now we come to airflow. Airflow has to be one of the single most important yet overlooked parts of the heating or cooling system, no matter when they're being put in. And that's a shame. Guys like myself that have been in the industry for a long period of time, yet started clear back in the 90s or 80s or before, may have never actually had the proper teaching to learn how to check airflow, to properly learn how to use a blower performance chart or a manometer to aid in their diagnostics for airflow. We're going to talk about that right now because I place a fundamental core value on this subject. So in looking at airflow, there's a couple of things you got to think about. First of all, you've got to make sure that the filters are correct. They've got to be the correct filter for the application, the correct size for the application. If either of those things are wrong, it doesn't matter where you have things set. You may not have the proper airflow no matter how you look at it. You've got to make sure that the filters aren't too restrictive. Now, there are some filters that came out in the late 80s, maybe mid 90s. We used to call them Paul Harvey specials. They were washable filters, extremely tightly woven, crosshatch with plastic mesh with some foam in between them. They were so restrictive that you could literally take and put a water hose up next to it and nothing would come out the other side, maybe a little drizzle. So you know airflow is not moving through there. Restrictive filters are probably one of the easiest things to correct on the job site that will make the biggest impact on the customer's comfort level. Is the blower wheel clean? Now, ASHRAE and Energy Star both place a number on the percentage of decrease in airflow on the return side or the supply side as to whether or not it's going to affect the rest of the system. And that's 10%. A 10% restriction on either the supply side or the return side, both can be affected by the blower wheel, can affect the overall efficiency and capacity by up to 50%. That is so huge and such an easy thing to fix and to cure as well. And you think about it, 10%. That's a dryer sheet getting stuck in the filter. That's a restricted secondary heat exchanger that rests above the blower wheel. That's the blower wheel itself, those little scoops that have barely a turn on them, getting a little bit stopped up with dust or hair. Those things make a huge difference. And if you've got to dismantle that blower housing, take the motor out of there, take the wheel off the motor and wash it out, and that's going to be the difference for the customer, you've got to take care of that. Is the evaporator clean? We don't have as many evaporator issues now as what we used to because we have a secondary heat exchanger now that rests just above that blower. And so oftentimes the secondary heat exchanger is going to catch all of the junk that used to get caught in the evaporator coil. However, anything that gets past there that's a much smaller particulate, like dust and pet dander and things of that nature, are going to catch on a nice wet coil. So the evaporator coil can still get dirty, and especially if you're using filters that are the least amount of restriction, which are those fiberglass filters. You know, that's what the manufacturer gets the efficiency ratings with. That's what gives you the best airflow, but that also, on the opposite side, is the least effective on the filtering side of things. But you can't take that into consideration because these furnaces were never meant to filter the air. They're meant to move the air so that we can create a comfort level through our heating and cooling system that's sufficient for the customers and efficient for the home. Are the registers open? Well, think about that. If you're only closing 10%, the average home has somewhere around 25 to 30 registers. That's 3 registers in a home that are closed. Probably most of the homes that you go in will have registers closed in them. It doesn't take much to create a negative effect in closing those registers. If you're not able to move that air down those runs, that does impact everything else. Now think about it. People close off the registers in order to attempt to force the air in a different direction or to a different portion of the house. Okay, true. Now, if that's the case, wouldn't it always work? Well, that's a loaded question. That's a tough one. It depends on the type of blower. Now, if you've got a multi-speed blower, the multi-speed blower doesn't know that you've closed all those registers. It's still trying to push down those runs. And just because you close off those registers doesn't mean the airflow is automatically going to go to a different run, say to the second floor or to the weird bedroom above the closet or to the new addition that you've put in that never had good airflow. It just doesn't work that way. The variable speed technology does help in that a little bit, but if you're restricting that airflow by closing the registers, you have unintended consequences of doing that with a variable speed blower, because once you start restricting that, the amp draw goes up and it starts to cost you some more money. And that's originally why you got that variable speed blower in the first place, was one, to push the airflow, of course, but two, to save you money. No, it's only going to save you money if it's in the proper application, and restricting it is definitely not the proper application. So look at this blower wheel. I've got a couple of fun pictures here. This was an actual picture that was taken by one of my good friends in the technical department of a wholesale house. He goes out to a customer's job site because the customer wanted to claim warranty on an air conditioning system that had a coil that continued to freeze up. They'd gone through a couple of different expansion valves. They pulled the coil out. It's not stopped up. So here's the long story short. Customer has an existing furnace. The old air conditioning system wasn't working properly, so the contractor sold them on replacing it and putting in a new air conditioning system. This was a condenser, a coil, line set, expansion valve, all of that. So they get the job done, and when the job is done, the new system is working very similar to what the old system was working like. And that was obviously a problem for the customer. They just got done spending a ton of money with the contractor, and the contractor was at a loss. So they replaced the expansion valve more than one time. And finally, they just wanted warranty on the whole thing, wanted their money back. They wanted to go with a different brand. And so the technical advisor gets involved, goes out there. First thing that he looks at is the surroundings, right? What's around that coil? What's around that condenser that could affect the way it operates? You know, and this is just it's a different mindset. Some people don't think that way, but the problem isn't always with the mechanical appliance that is showing the problem. Sometimes the problem is with the surroundings. And so he begins to look at some of the surroundings. And one of the beginning things, of course, was the filter and the duct work and all of that. But then he opens up that bottom panel and looks at the blower, and the blower wheel is completely full of hair. Now look at this thing. That's pretty next level. And so at that point, obviously, the contractor was a little embarrassed. But think about this from a homeowner's perspective. Now, how would you think that contractor treated you? If that contractor was having problems with the old air conditioner and couldn't get it fixed and replaced it, and the new air conditioner is having the same type of problem, which was freezing up and airflow issues, and then you see this, which directly ties into both of those issues, maybe you're thinking that you got sold a bill of goods, and you didn't actually need the air conditioning system in the first place, and it was a simple maintenance related issue that could have been solved, or that could have solved the problem much less expensive. That's a conversation I don't want to have, and I'm sure that you don't either. Here's another fun picture. Now this is fun for us, but it wasn't fun at the time. This is just the opposite. Here we have the technical advisor going out on a job in which the furnace, brand new furnace, kept trip and limit. Nothing that they could do to get this thing to quit trip and limit. Well, it was your standard installation in which the furnace was going to be replaced, but not the coil and not the air conditioning system at all. So what they did is they go out there and they strap up the plenum with wire, so that way it stays in place as they pull out the furnace underneath. And rather than just stick your head under there and look up to see whether or not that coil has stuff that you could clean out of it while it's now wide open, they didn't do that. They got ahead of themselves and moved much more quickly than what they should. And instead of finding this mess, what they actually did is just shove the new furnace under there, left that coil where it is, didn't check it out, and built the plenum down to the top of the furnace, and then ran the furnace. Couldn't figure out why it tripped limit. Well, it couldn't get rid of the airflow, and that's a big problem. When you can't get rid of the airflow, you can't get rid of the heat. So you've got to think about those things when you're out there. Think about how quickly this problem could have been solved during that installation. Now, sure, it might slow you down for 10, 15 minutes while you clean this thing out, but that's not nearly the amount of time that was spent afterwards in the several trips and also getting the technical department and almost the manufacturer involved with the situation and getting egg on your face because in reality, the problem was yours, not the equipment at all. So checking the airflow. And here we are talking about air conditioning systems and checking the airflow. And we hear terms like external static pressure or ESP thrown around all the time. So what does that actually mean? Well, ESP, the external static pressure, basically static is a fancy word for resistance, right? So we're looking for resistance external to that furnace. So everything that is before the furnace, including the filter and all the ductwork, and everything that's after the furnace, including the coil and all the ductwork, are all included in this measurement. Now, if you look at where the two white holes are in this furnace, they could be symbolic of the side of the furnace or the back of the furnace. You could make those two penetrations actually in different spots. I've seen people, and I myself have gone in through the high limit switch, remove the high limit switch. We're not running this on heat or cool. We're only using the fan auto speed or potentially just setting up dip switches. So you could go in through the high limit switch, and I've seen people go into the before the blower section with taps that go in through the low voltage side of that cabinet. So there's other places that you could go. This is symbolic really to show you that you have to take a measurement before the blower, you have to take a measurement after the blower, and that's got to be in the furnace cavity, so it can't be outside of that. So what is that going to actually do? That's going to show you on your manometer how much resistance is placed on everything after that furnace and before that furnace. How much stress is that blower really under? Because the manufacturers have a specific value that they're looking for. Almost all manufacturers across the board are going to give you a value of 0.5 inches of static that you're shooting for. Okay, but if you look at this chart that we have here, that 0.5 inches of static is on the right hand side of center. You could actually go up to 0.8 inches of static on this, as well as most other manufacturers that have multi-speed blowers, and still be within a verifiable range. And the idea here is to check the static before the blower and after the blower, add those values together as raw numbers, take them over and to this chart, and plot those across the top of the chart. Okay, so we've got 0.5 inches of static and I'm on low speed. Well, I'd have 674 CFM going through that air conditioner at that furnace at that time. So that's the kind of value that we're looking at there, and we're going to explain this a little bit more, but really this is, in a general sense, some of the baseline information that you've got to know in order to properly set up your furnace. So looking at a blower performance chart, this is another version of the blower performance chart in which you see what's called a fan curve. Those two weird lines in all the checkers there are telling you where that fan is operating as far as CFM goes and static goes throughout the cycle of that fan operating. Okay, so if you look across the bottom, you see the CFMs. Okay, that is airflow and CFMs. We know most manufacturers want you to set up an air conditioning system to operate at 400 CFM per ton on most. Some of them are at 350 CFM per ton. But if you look at the 400 CFM per ton, what that's telling you is a 1-ton unit would use 400 CFMs. A 2-ton unit's 800. A 3-ton unit is 1200 CFM. And you're trying to set it up for that value. Okay, so how do you figure out where that actually leads? Well, if you were to use your manometer and stick it in those areas of the furnace that you made the penetrations in before and after the blower, like we just talked about, you'll find a resistance reading. And on that resistance reading, you then take that back to the chart, and that chart is going to tell you what the CFM value is for that resistance. Okay, and before we move off of this chart, we're gonna talk about this a little bit more, but before we move off this chart, there's something that we really need to address, and that is filters. Okay, one of the biggest problems that we have, we go out and we put in a brand new furnace, and that brand new furnace is set up to the nines by the efficiency programs that are out there, by the standards that the manufacturers give and the industry gives. So we do everything right. When we leave, the customer goes out and buys a $30 really restrictive filter, puts it in place of the one that we have, which is probably going to be either a 4-inch filter or it's going to be a fiberglass type filter. And they totally change all the dynamics because they've really restricted that airflow now. And because they restrict the airflow, the charge isn't going to be adequate. It's going to change the temperature drop across a coil. It's going to change the delivery to the different rooms of the house, all of that. So how do you explain that to a customer? You know, unfortunately, I don't have a good way that you can do that. However, I do have a suggestion that you can get into your own mind, and this may help you come up with a way that you can explain this to a customer. Okay, so bear with me. On the left-hand side of this chart that you're looking at, you see numbers going up and down, and that's what's called static pressure. It's measured in inches of water column on a manometer. Now, static pressure is a fancy word for resistance. How much resistance is in that ductwork, and that's what you're measuring with your manometer. So going up and down that chart, as you go all the way up to the top and you see the number 1, that is 1 inch of static. In most applications, that is way more than you would ever want. Okay, but in this particular example, that's the maximum amount. You can't get any more than that. Okay, but at 1 inch of static, if you were to put a dot right on that line, clear over by 1 inch of static, how much CFM do you have? You have 0. So at the most amount of resistance, you have the least amount of airflow. Now look at it from the other direction. Go down to the bottom horizontal chart. You see those numbers across the bottom, which is CFM. That's how much air is actually moving while that fan is running. The farthest you can go over to the right, let's just say it's the 2200. Okay, you go over to that 2200, that's the fastest this thing is going to ever run. That's taking the blower out of the furnace altogether and setting it out on the floor. It's equally as bad for the motor. It's going to burn itself out because it's freewheeling, but you get my point. Least amount of resistance, so we got 0 resistance, is the highest amount of airflow. So look at it this way. If we put a board, a piece of wood, in the filter box, it's going to catch 100% of all of the pet dander and allergens and dust mites and hair and everything you could think of. It's going to catch all of it. It's a 100% efficient filter. Now, how much airflow is moving through there? 0, right? So we got a 100% efficient filter, but 0 airflow is moving through there. So the closer you get to a piece of wood, the more efficient your filter is going to be, but the worse off your airflow is going to be. And your system is only as good as the airflow. And with airflow being the biggest issue in our systems, you want to have as little restriction as possible with that filter. Now, with that being said, that's a hard conversation to have with a customer. They want the best filter because they want to filter all the stuff out of the air. Unfortunately, sometimes they're willing to jeopardize their $8,000 or $10,000 install with this equipment on a $30 filter because it's a better filter. These systems were never designed to filter the air. Now, there's a reason you can't go down to your local hardware store and get a filter with the same name as your furnace in a 1-inch filter, because those restrictive MERV 11 filters may not be the best thing for your furnace. So you go down to True Value, you might not find a Goodman 1-inch MERV 11 filter. You might not find a Carrier MERV 11 1-inch filter or a Trane MERV 11 1-inch filter because they weren't designed to be in these systems. These systems get their maximum efficiency by allowing the most amount of airflow to go through there, so they move the most amount of air while having it at the right temperature when they're doing it. That helps dehumidify and cool in the summer and heat in the wintertime, but it also, on a larger scope, over the long haul of this system's life, it will preserve that life. It won't be working as hard. It won't sweat in places it's not supposed to sweat. It won't have problems that go unseen for years and years that will eventually lead to large, expensive problems. So blower performance is a huge, huge factor in everything that we do. So here's a more expanded blower performance chart as far as your static pressure chart. If you look over to the left shows you the model of the equipment, and you have to make sure that you're looking at the right model. Okay, for instance, the one that's up at the top there, the GMH 95045-3BX. It's telling you that you've got your fan speeds set at medium and high. Okay, so your medium is going to be your furnace speed on high, and then your high speed is going to be your air conditioning speed. Is that going to be good for every application? Do you just not set it up after that and don't need to check it because the manufacturer knows what they're doing? Well, no, that's not the case at all. That is a very specific setup that's there for the manufacturer, and the days of leaving it the way the manufacturer has it, okay, those are gone by the wayside. So you have to check it. You have to put your static pressure tubes in there, and you have to check everything. Okay, so you check before the blower and you check after the blower. And once you check before and after the blower, then you make your assessments. You add the raw numbers together. Okay, now for those of you mathematicians, that might be a bit of a tough stretch, right? You stick it before the blower, it's sucking, so it's a negative pressure. You stick it in after the blower, it's blowing, so it's a positive pressure. We don't care about the negative and positive. You take the negative and positive, you crinkle it all up, and throw it in the floor because we're adding raw numbers. So in this instance, if you measured your static pressure and it was negative 0.4 before the blower and positive 0.4 after the blower, those don't equal 0 in this particular example. They equal 0.8. And if you look at our example here on this GMH 95, if we had 0.8 inches of static, and we were on high speed with this air conditioning system, we'd had 853 CFM. Now, is that the right amount? I don't know. It depends on what size the condensing unit is. Is it a 2-ton unit? Is it a 3-ton unit? Is it a 5-ton unit? Those are what make the difference. 400 CFM per ton. Now, what I like to do is when a system is brand new and I'm installing it for the very first time, I like to check the static pressure on each of those fan speeds and write it next to the fan speed. So that way, one, later on, somebody knows that it was done. And they see the values, they see the work done, they see the penetrations, they know that I did my job. Two, it allows me to come back and make adjustments knowing what those static measurements are. I can quickly see all the CFM values that correlate to the static measurements. Now think about it. You've got 0.8 inches of static on your high speed. Chances are going from high to medium, you're going to be probably somewhere closer or in between the 0.7 and 0.8. Okay, so let's say it drops down to 0.7. Well, check that out. At point 0.8 on high speed, it was 853 CFM. But at point 0.7 on medium speed, it's 859. It's actually 6 CFM higher on medium speed because of the change in the resistance in the ductwork. Now you go to medium low, chances are between medium and medium low, you probably won't drop to another static level. So it'll probably stay right in that same guideline there. So you probably drop down to maybe around 741 in this instance. And then once you drop down to the low speed, you're going to be at that 620 CFM range. And those are examples. Those are not standard by any means. You know, there is no such thing as standard. Every install is different. Every piece of ductwork in every home is a little bit different. Now think about this. Okay, I'm going to switch gears and I'm going to tell you something, and it's going to correlate to heating, and I think you'll get it. Right? This is how critical it is that we set these up. In the past, some of the older furnaces that we put in had an air temperature rise nearly 100 degrees. Okay, now you take the same BTU value in today's furnaces, our air temperature rise, according to many of the efficiency tests and setup charts, they want you to be somewhere around the 50-degree temperature rise setting. Okay, now the manufacturer has on their tag 35 to 65 or 30 to 60. Okay, but that's an operating range that's safe to operate that piece of equipment. That doesn't tell you anything about efficiency or anything like that. You still got to set it up. Okay, so older furnaces had a temperature rise of around 100 degrees. Newer furnaces of the same BTU value are supposed to be set up around 50 degrees. So what changed? We went from 100 degrees temp rise on the old one to 50-degree temp rise on the new ones. A ton more airflow. That's what we've got to move, is a ton more airflow. So the older ductwork that's in the homes oftentimes is not sized correctly for the modern equipment. It was sized to move less airflow. So we're already starting off with our hands tied on the ductwork, because usually it's all in finished ceilings and walls and floors and things like that. So we have to do what we can to make the airflow right in the home. And what we can do is, one, make sure that the filter is sized properly, and also make sure that it's not restrictive. The fiberglass filters, although nobody likes to use them because, well, you can hold it up like this and see right straight through it, and it's not going to catch much except for the big stuff. Well, you start putting more restrictive stuff in there, then it starts to cut into your airflow and mess everything up. So we can control the filter. We can control the filter both in size and restriction. We can control the return air drop. One of the biggest things that I see as an issue in our industry are the return air drops. 20 years ago, one of the more common filter sizes was a 16 by 20. And there aren't very many manufacturers nowadays that will allow you to use anything smaller than a 16 by 25, up to 70,000 BTUs. And once you get above 70,000 BTUs, or at 70,000 BTUs, well, then you really need to jump up to a 20 by 25 filter. And then at 90,000 BTUs, you need to have a base with a 20 by 25 opening, or you have to have the weird dual side return in there, which always looks a little bit odd. But you've got to make sure that you have adequate return air, and that's one of the easiest things for us to cure is the return air side. Now, that doesn't count putting in more return air registers upstairs as being easy. I'm talking about what's in the actual mechanical room. And the last thing that usually is something that's fairly simple for us to cure is going to be the collars. 20 years ago, you had a lot more dedicated sheet metal workers, and those tinners were very, very good at their craft. And I'm not saying we don't have them now, but the price of prefabbed metal has come down so much that a lot of times, instead of making some of the easier, smaller parts out in the field, they'll go buy a box of them. And so they have them on their van, so it doesn't really, it's not really cost effective to make them like it used to be. Now, 20 years ago, if you had to put a collar on for a run that's coming off the ductwork, the tinner would go ahead and just fabricate that right there on the job, and it would just take him a few minutes to do so, but oftentimes it wasn't going to be an offset, right? So the offset comes off of the ductwork in a slope, right? So it slopes up and then out on your trunk lines. A lot of times in the old days, what they would do is they'd fabricate one that was a right angle, right? Just a nice square collar, which served the purpose just fine. We had less airflow back then, so we didn't have as much of an issue with the duct restrictions as we do now. So to sum it up on what we can fix and what we can do with our ducted systems to provide better airflow is, one, you go out there and you look at a job and you're bidding a job and you're putting in new equipment, or even on a service and check, look at the return air drop. You can get a lot of information from the return air drop. Is it physically sized right? Is it big enough for the return air on the new equipment? Do we have adequate filter space? Meaning, is it at least 16 by 25 or bigger? Now, with that being said, are we doing a 4-inch filter? If we're doing 4-inch filters have more surface area, so usually they lend themselves to better pressure drops, and they're not as restrictive as the 1-inch filter. So if you have to have something that's a little bit better filter, you know, instead of going with the 1-inch filter, which has very little surface area and is highly restrictive, you'd be better off to go with a 4-inch filter that has more surface area and less of a restriction in the system. Now, you're still going to have to change it every couple of months. So it's going to cost you still, you know, 20, 30 bucks to do so, but it will filter the air better, and you'll not bite into your airflow as much as a 1-inch filter will. So back on track, we got the return air drop. Is it sized properly? Do we have the right filter in there? And after that, do we have straight collars, or do we have offset or transitions? You know, how is our duct work coming off on our trunk runs? If they're straight collars, we can fix that easy. We can put in offsets. And then lastly, make sure that everything is set up properly. You know, do we have a blower? Is our blower set up the way that it should be? Do we have the right dip switches selected on a variable speed or ECM blower? And then in addition to that, do we have the right CFMs on a multi-speed blower for the amount of tonnage that we have on this equipment? Here's your example. If you look at this, we had 0.7 inches of static on high fan speed, 0.5 inches of static, taking your measurement, of course, before the blower and after the blower. Adding those together, that came up to 0.7. You go over to this chart, 0.7 equaled 955 CFM. Okay, so that is a direct value that is very easy to measure and then also to manipulate, because you can change your fan speed to one lower than that very easily. You just change the speed taps on the blower. Looking at the CFMs, again, when you're taking your CFM static measurements, you're dropping the negative and the positive off, and you're adding just the raw numbers. So like I said, negative 0.4 and positive 0.4, traditionally in mathematics, that would equal 0. But in what we're talking about, you're taking the negative and positive, throwing it on the floor, and adding the raw negative, or the raw numbers, which would be 0.8 in this particular instance. Your fan speeds, traditionally, as we were just looking at on the manufacturer's guidelines that I just had pulled up there a minute ago, you had 4 fan speeds. You had the high, you had the medium, then you had medium low, and then you had low. Okay, so if you look at this board, you've got a spot for your high heat, your cool, your low heat, and then there's 2 up in the top left-hand corner. They're called park. Park is not energized. It's a place for you to put any spare fan speeds that you don't want energized, and it's in lieu of the way we used to do things. The way we used to do things was to just tape it up and leave it hang, or strap it to another bundle of wires. Okay, now you just run that to the board, and that's an unenergized terminal. One thing that you'll find out, and once you start actually checking your blower speeds, is that your high heat and your cool speed will usually be very, very, very close to the same speed, and oftentimes will be the same speed. It's not the traditional way we used to do things. Traditionally, high was always cooling, low was always heating. Now they're pretty close to the same in most applications, and that's because nowadays we're doing load calculations, and the load calculations are very precise on BTUs for loss and gain on both heating and cooling side, and so it's an interesting thing once you get to starting checking these things. Now, I told you also that one of the things that I like to do is check all the fan speeds really before I begin my setup. Checking all the fan speeds on a multi-speed blower with a board such as the one that we're looking at right now is very simple. The cool terminal on there is what's directly connected to the fan on switch on the thermostat. So if I connected the fan on switch, or I jumped out the R and the G on the board, it would turn on the speed that's on that cool terminal. So as you might guess, what I will do is I'll put my manometer in those two penetrations, the one before the blower, the one after the blower, and I will go from one fan speed, turn it on, write down the static measurement, pull it off and swap it out with another one on the cool, and then I will go to that one and then write it down, and then I'll swap it out with a different one yet, and I'll go from one to the other on that cool terminal, turning the fan speed on, so that way it's very, very quick. I'm not using heat or I'm not using cool. I'm just looking at the raw values for the static and the ductwork. Is all I'm looking for, so I can properly set up that blower. Okay, and there's a little bit closer look at what we're talking about. Okay, this one's a little bit different because here we actually have a control board for a more advanced system that has an ECM motor or a variable speed motor. And you can see on the left-hand diagram out of the manufacturer's installation instructions, there's some switch banks there. And ironically, the way that those are labeled is S1, S2, S3, those are switch banks. And they don't necessarily always work out that way. As you look at the actual control board that I took a picture of here on the right-hand side, if you look close in the upper left-hand corner of each of those switch banks, they're not in order. The one at the very top, spaced away from the other three, is S3, so switch bank 3. Then after that comes switch bank 4, and then 5, and the one very, very lowest on that totem pole is switch bank 1. Now you can see that those switches on those switch banks, they go in one position to the other position. One side's on, one side's off, and different configurations of on and off give you different values in programming for how the controls in the rest of that furnace operate, particularly in this case for our variable speed motor. Okay, here's an example of the manufacturer's diagrams on how to adjust the blower speed. Okay, if you look at the switch banks at the top, we got switch banks 1, 2, and 3. And if you look at the cooling selections here on the little breakaway chart, just off of the left-hand side of where I am, which is right over here, you'll see the cooling selections. And they tell you whichever size blower you've got, that's going to be the corresponding CFMs for your configuration of dip switches. Okay, so if you've got the 56,000 or the 70,000 BTU furnace, then you're going to have a half horse blower, and your configurations of switch bank 1, dip switch number 4, and dip switch number 5, both in the off position, will be 1,050 CFM. But if you had the larger size furnaces, the 84,000 and 98,000 BTU furnaces, then you're going to have the 3/4 horse blower, and that same configuration of dip switches, switch bank 1, dip switches number 4 and 5, will then equal 1,750 CFM. Okay, so you have to make sure that you've got the right blower that you're looking at here as far as your terminal settings and when you set up your dip switches for an ECM motor. Now, it's not rocket science. And some people set these up and they say, well, how do I know that it's actually achieving that? Okay, well, here's a secret. These things are pre-programmed to achieve the CFM value that you set them at as long as you're less than 1 inch of static. So that control module that's on the end of that motor will maintain that 1050 CFMs on the off-off configuration for the half horsepower blower unless you go over 1 inch of static. Okay, so your measurement before the blower and after the blower has to be less than 1 inch of static in order to maintain that 1050. Now, once you get up above that 1 inch of static, it goes all over the place. It's just, you can't say that it goes down, it goes up. It's kind of a mixed bag. But one thing's for sure, the farther away that you can keep it from 1 inch of static, the better off you are. Now think about it. Okay, you've got a motor with a computer module at the end of it. And that motor with a computer module at the end of it is consistently trying to fight the resistance in that ductwork. And the way that it does that is it's changing its configurations internally to increase the amount of torque that it can exert against that resistance. In doing so, the amp draw goes through the roof. So you've got a motor that's extremely efficient as long as it's in the application that it was designed for, which is 1 inch of static or less, and according to manufacturer specs, 0.5 inches of static or less. If you put it in that application, it will run much more efficiently than its counterpart in multi-speed blowers. And again, here's your blower chart. Your blower chart that we just spoke about a second ago. Not a lot of rocket science here. I did want to make sure that we got one more look at it so that everything was crystal clear. Okay, so things you need to look at. You got your correct model number, okay, over on the far left-hand side here. You're on X fan speed, and that X fan speed correlates to your resistance across the top, right? Your static. So that would be the 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Okay, that's your measurement of before a blower and after the blower, and you add the raw numbers. Okay, once you figure out what those are for each fan speed, you go to that static resistance, go down the column, match it up with its corresponding CFM value, and set up your blower according to 400 CFM per ton for this manufacturer, and for most manufacturers, or 350 for just but a few of them. But know what the manufacturer actually wants and set up that blower speed according to that. If you don't do that, what happens? If you don't set up your blower speed properly, well, then what? I'll be honest with you, I went over a decade not understanding any of this stuff. So what happens? What happens to those air conditioning systems? Well, almost every one that comes from the manufacturer has high speed as your air conditioning speed. Okay, so if high speed is your air conditioning speed, and that's way more CFMs or airflow than what the system actually needs, what happens is it makes your coil too warm. It takes the cool away from your coil too quickly, so you don't get good dehumidification, you don't get a good air temperature rise, or I'm sorry, air temperature drop across that coil. So what you do, instead of lowering the blower speed like you should to the correct CFM value, you go out and you add refrigerant to the system outside. And when you add refrigerant, it fills that coil a little bit more and creates a little bit better temp drop. Never perfect, but in doing so, it gets it to the point to where it's working fairly well, but over the long haul, here's what happens. It doesn't dehumidify properly. You've now overcharged the system, so it's not running efficiently. You've ruined some of the capacity, some of the efficiency. The compressor is not running, electrically speaking, as efficient as it should. It's going to draw more amps on startup. So the likelihood of it tripping a breaker or blinking the lights is much higher than what it would be if you'd have just done it the way that you should have done it. And all around, those things are going to probably add up to a system that dies or has a failure rate well before its time. And the best case scenario, you're going to have a system that is going to cost the customer a bunch of money over a long period of time because it's not running as efficiently as it should, and it doesn't have the capacity to now cool the entire structure the way that it should. So it always will struggle. Okay, so here's another little secret. Those problems only show up in extremes. You ever wonder why it gets so busy when it's 95 degrees, but when it's 87 degrees or 85 degrees, it's not really all that busy at all? Well, because at 85 degrees, you turn a box fan on in your room, a box fan feels pretty good. You can cool a home that's at 85 degrees at least enough to make the customer or yourself feel like everything's working the way that it should. The wheels are all spinning, and not enough to complain, certainly, but once you get up above the 90s, into that 95 degree plus range, all the little things that you didn't do correctly when you were out there servicing it or initially installing it, that's when those things show up. The extremities. Your furnace problems always show up at below freezing. Your air conditioning problems always show up in the 90s and above, because that's when all of those problems are exposed. When it's 90 some degrees in the Midwest, it's also really humid. At 85, sometimes people still have their windows open and you get a nice breeze across the house. But at 95 degrees and humidity added into that mix, it feels like it's into the hundreds. So if you're not dehumidifying properly, because it's not charged properly and the airflow is not set properly, that sticks out. And then you run into a situation where maybe you have some cool air, but it's cool and it's clammy, so it's a little moist. It's not dehumidifying. You run into kind of a funky smell as well. My name is Corey Paper. We're going to go over the adjustment of a blower in a gas furnace. And in doing that, what I've focused on is how simply changing the blower speed to set it up properly for the manufacturer's guidelines to make sure that you've got the proper CFMs going across this coil for air conditioning and across this heat exchanger for heating makes all the difference in the world. Now, traditionally, we have always been told or have assumed, some of the old school guys like myself, it comes on high from the manufacturer for air conditioning speed, it comes on low from the manufacturer for heating speed. We just leave it there. And that's not the way that we are supposed to do it. It's not the way we're ever supposed to do it. And so that is why I'm going over this. It's a very simple process. It's called checking external static pressure, or ESP. Static pressure is just a fancy name for resistance to the ductwork, and that's what we're checking. And some people can make it very complicated. Other people can make it as simple as it could possibly be. For me, I have a pretty simple method for checking that. Okay, first of all, you've got to take your measurement with a manometer before the blower and after the blower. Okay, some will say after the filter and before the coil. That's the same thing. The main thing is you don't want to take it before the filter and after the coil, because the filter and the coil oftentimes are your most restrictive devices inside of that ductwork. So you want to make sure that you're compensated for those by looking to see what they're actually drawing as far as resistance in this system. So in setting up your blower speed, we can see we've got a manometer right here, which is hooked up inside. Set that up here for a moment. Take off this bottom door. And I have removed the blower speed taps to make it quick and simple off of the board. Okay, so we've got several different areas where things hook up on this board, but what we're most interested in on this particular setup, where we've got a multi-speed blower, not a variable speed, there's no computer modulating system on the end, but just a regular multi-speed blower, we're going to change the speed taps, which will change the speeds. If you'll notice, right on the back of the data plate, we actually have the different speeds and the colors that correspond with those. We've got black is your high speed, blue is your medium speed, orange is your medium-low speed, and then red is going to be your low speed. Now what we're trying to figure out is which of those speeds is going to be the proper setup for this furnace for the air conditioning speed. Now in doing that, we have to make sure that we set everything up properly according to the manufacturer's guidelines. And the manufacturer's guidelines tell us that we've got to make sure and set it up according to the blower performance data, like you see on this chart. The particular furnace that we're working with is a GMH 9545. You can see it says high, medium, and low speed. We looked at the colors just a second ago so that we were adept at looking inside of the bottom of this blower compartment and seeing those colors. Across the top here is your actual static measurement, and that static measurement is going to correspond to an airflow noticed right below, CFM. What we're trying to do is set this up properly for the manufacturer. Down at the bottom, it actually tells us in order to be set up properly for this manufacturer, we want 400 CFM per ton for cooling for this setup. So we're going to try to find that. But right now, I have already set this up. So I know that we're set up for the proper blower speed right now as it sits. As you'll notice, we've got the orange wire in here. The orange wire is actually the wire that we're using, and it's low speed, and that's because I've already measured this. I have my manometer already hooked up. I'm going to go ahead and put in a regular old filter. Okay, and these fiberglass filters are the ones that we're supposed to be using in a furnace. Even though most people use the Merv 11s or something like that, the manufacturer uses the fiberglass filters. So on this medium-low blower speed, we'll notice that once we're hooked up and we've got the right filter in there, our doors put back on, that we'll achieve a certain amount of static that's going to get us in range because I have tested it. Okay, now normally what I would do is I would start on high speed. I would go through from high speed all the way to low speed, and I would set up each of those statics, write down each of those statics in the installation guidelines. But I want you to see firsthand what it looks like when we've got the proper airflow on a manometer. Okay, so I've just turned it to on. Should kick on in just a moment. And as it does, you should see somewhere within range on here what the value we're looking for is. Okay, so immediately it pops right up to where it's going to operate at. We're at about 0.51, 0.52. You round that down to the next or the closest number, just like anything else. So we're going to round that down to 0.5. If you look at the installation guidelines for the system that we're working on, we're on medium-low, 0.5 inches of water column, gives us 884 for our value for CFMs. We've got a 2-ton system we're working with, and as the manufacturer specified, we're looking for 400 CFM per ton. 2 tons at 400 CFM per ton would give us 800 CFMs. So we're right at that value we need to be at. But one thing that we could do to possibly mess that up just a slight amount is put in a more restrictive filter. I know most people use pleated filters. You got to remember, the pleated filters are not designed for these systems. There's a reason you can't go down to your local hardware store and get a filter that's designed by the manufacturer that made your system. As you can see, that definitely made an impact on our manometer. We went up a little bit. Now remember, this filter is brand new. There's no dirt on it. As it gets dirty, the more restrictive it's going to get. And it'll get dirty quicker. The fiberglass filters that we were just looking at won't hardly catch enough stuff that it'll get stopped up within the 30-day time frame that you're going to leave that thing in there with. Okay, so we're going to go ahead, take this filter out that we just put in there. We're going to put the fiberglass back in there. We're going to change our blower speed. So when changing our blower speed, we're going to get inside of this blower compartment again. Wait for this blower to kick off. Once it kicks off, we're going to go right back up to that high speed that traditionally is where a lot of us have these already set up. I'm going to go ahead and take it off that medium low, which is where we know now that it's supposed to be set up. Okay, so now we have our fan back on. With our fan back on, we can see that high speed has jumped this all the way up to just over 0.6. Right, 0.63, 0.62, somewhere around in there. What does that mean on our CFM? Because that's traditionally where the manufacturer would have left this, would be on high speed. That would be the manufacturer factory setting. So in looking at this, what would high speed have meant? Well, high speed at 0.6 inches of static would be 1,044 CFM. Way too much airflow for what we're looking for. So that amount of airflow would mean that we wouldn't get the right amount of cooling for what we're looking for. We've got to have somewhere around 800 CFM per ton. So that 800 CFM per ton is super important. If we left it on high speed and went in and checked our temp drop across the coil, we would notice our temp drop across the coil wasn't very good. We would also notice when we're checking our charge that our superheater subcooling would be off depending on the type of metering device that we've got. So we would have to go back and adjust the charge to compensate for the poor amount of airflow. And all we've talked about here is setting up the blower. If the blower's not set up right, nothing else will function correctly. We still have to have the proper size filter. We have to have the proper type of filter. Our charge has to be good. Our ducts have to be clear and open. We have to have enough return air. There's a lot of stuff that goes into this. But it all starts with the blower. If the blower is set up properly, you can work with everything else. I do think that there's a lot of value in understanding some of the basic concepts behind efficiency and how it applies to the workplace. Efficiency has taken all kinds of steps from the beginning of our creation of air conditioning and heating to where we are right now. So what kinds of forms have been used? What forms of efficiency have we been talking about? Well, it really is kind of a loaded question when you talk about efficiency. Think about that. How many different forms can you think of that you've seen in your career that deals with efficiency? Well, there's all kinds. There's a manual J, there's forms that you got to fill out from the manufacturer, there's forms you got to fill out for the municipalities, rebate forms, all kinds of stuff. So there's no shortage of forms or paperwork involved in proving efficiency, but let's go beyond that. When it comes to efficiency, let's not look at it as something that is a burden, something that we're required to prove, some thumb on our neck that somebody's putting there to say, hey, maybe you're not doing your job. I want you to prove that you're doing your job to me. Don't look at it like that. How do I want you to look at it? Well, it's pretty simple. I'm a people guy. I'm a soft skills guy is what they call it. I really believe in listening to the customer. And that's not such a common trait nowadays. The customer will tell you all the issues they have. And a lot of times in those issues are hesitant for change. So they're already going to be kind of fighting the process if they have to replace equipment. And a lot of them are monetarily bound. They don't have a lot of money to spend on this stuff. What does that tell you? Well, that's a tough spot to be. If you don't want new equipment, and when you get new equipment, it's going to cost you more than you can afford, it means you're probably going to have to finance it. If you're going to have to finance something, then certainly you want to make sure that you get what you're paying for. As a person, as a service technician, this is what I've done my entire career. I run out, I do service calls. These days I do efficiency tests and I do some training and things like that. But really it all goes down to how you treat the customer. You treat them like you want to be treated, which is an old cliche. But if you do that, you're going to come out on top. You're going to stay employed because we're in the people business. You have to care about the customer getting what they paid for. Now, I realize that through most of our careers, we've gone out to a job and whatever furnace was there, whatever air condition was there, if it failed, we'd replace it with a like size, like load, maybe an upgrade in efficiency, but if it's up to the customer and it's up to pricing, maybe not. So if we go out there and we see what's already there and the customer's unhappy with its performance and we go back and we put in exactly the same thing, they may be equally unhappy with the new performance. So we have to make sure that what we put in is appropriate for the size and the environment that it's put into. We have to make sure that whatever we're putting in works as efficiently as what the manufacturer says it should and what the industry says it should. And really, there is no best way to do that. I'm going to tell you that right now. There's a lot of different ways for somebody to come out and prove and test efficiency, and this is just one. It's not the right one. It's not the only one. It's one of many. And the reason that I've chosen this particular subject to go over is so that you can have a different view, a different point of view, right? For most of my career, we've gone out, we've done the work, and the customer pays us. We're supposed to be the experts, and we leave. And oftentimes, there's nothing to verify that what we did works any better than what was already there. There's no steps that go into place. Sure, we've got some setup procedures we go through, but can you honestly say that we've checked and verified the efficiency of the equipment that's sitting there, that you've set it up properly? You've set the firing rate, you've set the blower's performance speed, you've actually done the calculation that tells you what's the current efficiency on the side of the house right now as it runs. Because that's what's really important. And that's what I'm trying to get across to you. This may not be the perfect way to do it, but it is a way, if you don't have another, that allows you to fairly quickly go through, check some things, that puts yourself into an accountable position and allows you to see, am I actually doing things the way the manufacturer said I should? Am I up to industry standards? Is this customer getting the worth that I promised them? That will set you apart in this industry. So let's look at some of these forms. Now, again, there's quite a few, and there's quite a few you may not have seen before. Here's the first one, a WX17 form. This is a form that's used by many state offices, and what this is for part of the weatherization program. Okay, so weatherization programs are designed to make sure that people that may or may not be able to afford to have energy efficient stuff put into their home or verified can get such done by qualified companies and maybe at a discounted rate or free rate. And if you look at this form, it's fairly comprehensive. There's a lot of stuff on here that's dated, but there's a lot of stuff that's fairly standard. So let's just break it down really quickly. So here's what we've got. Okay, it's titled the Mechanical System Inspection Clean and Tune. Okay, so somebody that has qualified for this government program, this weatherization program, has now had somebody call them, set up an appointment to come out and check several things within their home to make sure that they operate safely and that they operate as efficiently as possible. And these are the things really that are covered in that form. You've got your agency information, who the inspector is going to be that comes out. You got client information, what type of equipment do we have, and we've got all kinds of things that we've got for check boxes that are requirements for specific types of equipment. Then you've got some actual information, stuff that you've got to check, that you've got to measure. Okay, you've got airflow. Okay, airflow is a valuable thing to measure. Why is that? Well, because we can put a value on that. We can put a number on that. We know as an industry standard that if you're setting up an air conditioner or checking the air condition blower performance, you should be at about 400 CFM per ton as an industry standard, or there are some manufacturers out there that are at 350 CFM per ton. Verify which one that you're working with. But 400 CFM per ton is pretty standard and pretty easy to comply with. We're going to talk about that a little bit. What electrical information are you required to get? Well, it depends on what you're checking. You may have to get the incoming voltage. You may have to get the amp draw on certain appliances. What types of refrigerant lines do we have? What size? How long do you think they are? Are they exposed? Do we have insulation on those? How do they go through the wall? And visually, you'll inspect that combustion chamber. So in the furnace, what does the actual combustion box look like? Is it an older furnace that has cast burners with all kinds of rust and possibly soot in there? Are they newer style burners where you've got a combustion chamber with ribbon burners or in-shot burners and it's in fairly good shape, but very little adjustments if you had to adjust? What do they look like, physically speaking? Okay. You also have requirements to educate the customer. Now, what does that mean? This is one of those topics that folks get a little bit uncomfortable with. They call it soft skills. Okay, educating the customer is just as important as any other part of your service and check or your efficiency check. The customer doesn't need to understand everything you're doing. You're the expert. But they do need to know that there's value to the process you're using, that it will benefit them for you to check these things. Having the customer involved in that process makes it all that much easier. So part one on that form, that WX17 form, it's your agency's form or agency information and the type of job that you're going on. If you can see there, you've got some check boxes. You got the name of the person that's coming out and doing the inspection. You got related job numbers, things that it's going to require them to put down so that they can be recalled later on. Those types of things. What type of heating appliance is it? If you're checking a heating appliance, those types of things. Part two, quick checklist. You've got all kinds of things that you're going to be required to actually test while you're out there, right? You've got combustion units. You've got boilers. You've got furnaces and console heaters, air conditioners, water heaters, all kinds of things that could potentially need to be checked. And in a lot of cases, many of those combinations need to be checked on a job and by the valued expert that comes out to your home. Next, you've got the airflow system. Okay, so airflow is checked a little bit differently on this form than other forms, right? They require a lot of information on here. Now, we're going to talk about airflow here in a little bit. We're going to break it down. What makes it easier to understand? What makes it easy to check and verify? And what parts of the system really are the most valuable parts of the check? You've got things on here such as external static pressure. Okay, what is external static pressure? Well, it's the resistance on everything outside of the furnace, right? So the resistance from after the blower pushing through everything, including the coil, and the resistance from before the blower pulling through everything, including the filter. So that check is actually done before and after the blower, and those numbers are added up, and you're going to get a value there. You've got pressure drop across the coils, across the filter, things like that. What do those actually mean? And understanding what those pressure drops mean and how they fit into the equation is important, because that's more of a diagnostic side of things rather than a setup side of things. Okay, depending on how you look at it, you've got temperature rise and all those kinds of things you're taking into consideration as well. Part 4 is your electrical measurements. Right? Some of this stuff is visual, some of it's actual measurements, and there's all kinds of places out to the side to take notes. So this is also another valuable part of what you're looking at. In order to get the EER rating, or the efficiency rating of a unit as it's running right now, an air conditioning system, you have to be able to take your incoming voltage and your incoming amperage and get your wattage from that so that you can get that efficiency value. And we'll talk about that here in just a little bit. Next, you've got your refrigerant lines. Your insulated refrigerant lines. Are they insulated or are they not insulated? How long are they? Are they sized properly to meet all the specifications of the inspector or of the manufacturer? Are they routed properly? Are they too long? Are they too short? Too many 90s? Next is your tune-ups portion. Okay, here you're going to go through and check off boxes mostly that are basic everyday tune-up type stuff. You know, did you clean the flame sensor? Did you clean the filter or replace the filter? Have you done any calibrations on the thermostat if required? Have you adjusted any of the airflow? Okay, and then down below it talks about carbon monoxide testing and in the different chambers. Normally that's going to be for an older style unit or maybe even a boiler type unit where you've got more of either a positive feed heat exchanger or a gravity feed heat exchanger or something like that, a little bit different than what we have now, that you'll be able to actually look for differences in the combustion from one chamber to the next rather than a particular combustion mix. Part 7, this is your warm and fuzzies, right? This is your soft skills. And when it comes to soft skills, you know, it will do you diligence to really read through a list like this and ask yourself, do I do these things? You know, regardless if you're using this form or not. This is just an example. I'm not suggesting this, you know, WX form, which is very, very, very rigid. I'm not suggesting it, but I am saying there's valuable information on here. And if you want to get into the verification side of things, you have to figure out what type of checks and balances you're going to use to verify the work that you're doing. Okay, look at this warm and fuzzy part. Hey, it talks about have you educated the customer on how to operate the thermostat? Have you educated the customer on how the furnace is supposed to start and how it's supposed to shut down? Have you educated the customer on your filter? You know, not all filters are created the same. If they were, there wouldn't be so many doggone choices. And then, of course, one of the most important parts as far as administratively, the signature portion. If you don't have them sign it and you don't sign it, it never happened. That's your proof of the information that you've put down on that piece of paper. That's the proof of the work that you've done and their acceptance of that work. Very important, no matter whether you're talking about this form or any other form. You've got to have verification. Speaking of verification, okay, this is a verification form completely different than that WX17 form. This is just one more. This is a heat pump verification form that has been around for a long period of time. And of course, several states use this, several municipalities use this, and different variations, not this exact one, but going through this, you've got some of the same type of things that you're gathering from this. However, this isn't something that's put out there as an income-based form. This is something that's oftentimes put out as a verification form that has rebates attached, or potentially the ability to close out a permit on a job that's been permitted and then finished. If you look at this particular form, you've got your same portion at the beginning here, right? The portion that talks about who's your customer. Where do they live? What's your name? What type of equipment do they have? How big is it? What are all the particulars of it? Your next step, as you're going down through here, it's asking you for your CFM verification, right? You get your total external static pressure, you correlate that over to a blower performance chart, which we'll look at here in just a little bit. That'll give you your CFM. Or if you've got a variable speed furnace, then what you would do is you would set up your dip switches according to the manufacturer specs, check your external static pressure, and make sure that you are within range so that the end bell on that motor will maintain those CFMs, and then you're good to go. And if you look at the couple of different steps for verifying your CFM, they give you 2 steps, but really step A is the best way to go. It's the easiest one, less convoluted. And when you look at the capacity, look at that next step there in 6 with capacity. The end value that you're looking at there is BTU value, right? What's the actual BTU value that you're getting out of that piece of equipment? And that's been the end all be all for a couple decades. Right? We do these verifications, and it's not just about efficiency, but what type of BTU value is on this equipment as an end result of dum-dum getting involved with the installation. And if you go and continue on through there, there's a few other things that you've got to get, including your signatures, both from you and the homeowner. And my suggestion is the homeowner should have a copy of this, as well as your company, of course. And you're probably going to send it in someplace, so that's kind of a moot point. So we'll talk a little bit about this verification form, right? The newer way that efficiency is going is not based on rebates, right? The interesting tale that you get in the industry right now, rebates have been around forever. When you talk rebates, you're talking potentially the ASHRAE or AHRI rebates or something like that from the past that's based on the equipment that you buy. You buy high efficiency equipment, you get a rebate back from the state or local authorities or maybe even from your power utility. However, that wasn't the greatest program to have, because if nobody actually went out and inspected that equipment, then how do they know it was put in according to industry standards or according to manufacturer standards? They don't. So they just kind of give away free money based on what somebody purchased. So now the idea is we're not going to give you money based on you doing the job that you're supposed to do in the first place. But what we will do is we'll allow you to go out there, install the equipment, fill out some basic information that'll give us an EER value, which is a timestamp on the efficiency of the equipment as it runs today on the side of your house. If it fits the bill, we'll close out your permit. If it doesn't, you're going to have to go back to square one, figure out where things went wrong, and finish the job and make it run as efficiently as it should, right? So there's a little bit of additional information that you need for EER value verification. So one of the things that you need that we haven't talked about a whole lot is getting the watts, right? We talked about the CFM and the airflow, which are one and the same. So getting that is your external static pressure, going over to blower performance chart and correlating that by lining up two rows that gives you a CFM value, okay? Enthalpy. Enthalpy we didn't talk about a whole lot, but that's in both of these verification forms. And enthalpy is a pretty simple measurement to get, right? It revolves around the wet bulb temperature. Once you get the wet bulb temperature, you go over to an app or a chart and you measure a couple of values, bring them together, gives you an enthalpy value. Okay, that's your heat absorption. The BTU value was the end result of that verification we just looked at. You do all those measurements, you get down to, okay, I know I got a 36,000 BTU heat pump or air conditioning unit. What's the BTU value of it now that I installed it? Okay, is it running at 20,000 BTUs? Is it running at 30,000 BTUs? Because capacity and load and efficiency all kind of go hand in hand, and one bites into the other one. So we've got to know what we're doing there. But the modern efficiency check takes it one step further, right? It used to be SEER rating is what got you the rebate. You buy something high SEER, 18 SEER, 20 SEER, 16 SEER, you get a rebate. That's not the case in a lot of areas now. Now they're looking at the EER. Well, what's the difference there? Well, we'll talk about that here in just a second, but it's just huge. It's really huge. And in order to get the EER rather than just the SEER, you have to know the watts on the equipment as it's running. Okay, so that is another measurement that you've got to figure out. So here we are at the CFM, and we talked about this a little bit already. Okay, one of the most overlooked portions of the modern equipment has got to be CFM. We don't have enough airflow, we have too much airflow, you know, whatever the case may be. Normally, we have improper duct size. Now, why is that? Well, it's pretty simple. Okay, if you take it from a heating standpoint, older furnaces had a much higher temperature rise, meaning the temperature that it drew in through the filter compartment, which was basically from the rest of the house, right? So say 70-degree temperature, the temperature it drew into the furnace and then heated up versus the temperature that comes out the other side of the furnace that's already heated up. You subtract those two values, that's called a temperature rise. How much did it actually heat that air up? The older equipment had very high temperature rise, let's say 100 degrees. Now the newer equipment has much lower. Okay, 35 to 65 is a pretty standard in between as far as where your normal modes of operation would be, or your safe modes of operation would be. For efficiency's sake, many standards hover right around 50. So we'll say 50 for our example. If you have X furnace that's older and the temperature rise is 100 degrees, and you replace that with Y furnace that's brand new and the temperature rise is going to be 50 degrees. But the heating value is the same. So the old one was a 75,000 BTU furnace. The new one's a 75,000 BTU furnace. We have the same BTU value, but our temperature rise today is lower. What makes that happen? Well, you're moving a lot more air across there, and that is keeping the heat exchanger much more cool. Okay, so if we're moving a lot more air, the older ductwork is probably set up for the older furnace. And if that's the case, we're set up to move a lot less air than what we're actually moving today. But when people replace that furnace, they don't replace the ductwork along with it because that's one, financially, that's not a viable thing to do. You'd have to rip out portions of houses, walls, ceilings, floors, things like that. So occasionally you'll have somebody replace what's there in the furnace room, but even that is kind of a moot point oftentimes. So CFM is often overlooked because oftentimes there's not a lot you can do to change it, but there are some things that you can do to change it on nearly every job. We'll talk about that here in a minute. So airflow is oftentimes overlooked. We take out the old, we put in the new. We oftentimes think to ourselves, as does the customer, the old system worked just fine. It moved air from here to there just fine. The newer one should as well. Okay, so you've got to look for a couple of things to check the airflow, okay, or the CFM. You've got to measure the static or the resistance before the blower, but after the filter. Okay, so you can't do it out in the return air before you get to the filter. You can't do that because otherwise you still have that big restriction of the filter in there. So in order to take the proper measurement, it has to be after the filter where that air enters the blower compartment. And some people will do it right in the blower compartment itself, which is fine. Put a little static tip in there. Some will do it through the low voltage terminal that goes into that bottom panel. Some will do it through the back, the side. It doesn't make any difference. You have to get the resistance measurement in there, and that's going to be on the negative side of a 2-port manometer, or it's going to be a negative reading on a single port manometer. Makes no difference. Okay, then you have to take the second measurement, which is after the blower. Okay, now after the blower, but before the coil. So we're still staying inside of the cabinet of that furnace. Now, how in the world would you do that? Now, the way that I was always taught was simply take out the high limit switch, put a piece of tape over that hole, and stick your static measurement in there, and then run the fan on the on switch in order to take that measurement. Well, you can't really do that on all equipment nowadays, and I don't like to do things that you can only do on some stuff, and then not on other stuff. You got to change it up. So, in light of that, there's a couple of different ways you can handle this. Now, one, the efficiency tests have taught that even though I don't appreciate going through the skin of the cabinet of a furnace, okay, there are measurements that need to be taken from inside of there because that's where the airflow is moving before it gets to that coil. So oftentimes where we'll put that penetration to take the measurement after the blower but before the coil will be right below the air conditioning coil, the A coil, in either the sides or the back of the furnace. Okay, usually that's going to be 2 inches down, 4 inches over-ish. Okay, but tread lightly. Obviously, we don't want to damage anything making that penetration, getting inside of there. So before and after the blower is really the measurements you need. And now, of course, that after measurement is going to be on the positive side of a 2-port manometer, or it's going to be a positive measurement on a single-port manometer. Now, we're talking about positive and negative here. It's important to take just a second and remind all our mathematicians out there that the math behind this is different. You take the positive and the negative, and you crinkle it all up, and you shoot a basket with it. Right? It's out of sight because you want to add just the raw numbers, and that's it. Just the raw numbers. So if you've got negative 0.4 and positive 0.4, in the real world, that adds up to 0. In our world, that adds up to 0.8. And that's the way that we've got to take that that mathematics and do it. You do it irregardless of what the negative and positive measurements actually are. Okay, so in looking at airflow, okay, when it comes to airflow, we're going to talk about it in a little bit more depth, not a ton, right? We don't want to make it too overwhelming. It's a pretty simple concept. Potentially the most overlooked part of the system, we've talked about that already. We've talked about the ductwork oftentimes being inadequate. Not every time, but a lot of times. And people don't change it because some of the stuff you just physically can't get to without significant cost burden to the customer. So what could you do? Okay, as you're down there working on a furnace, what could you actually do that would make a difference? Well, that's an interesting question because there are subtle changes you can make that will make a difference, and it makes all the difference in the world. One, okay, the type of filter that you choose. Very, very few retro jobs will be fine putting in a 1-inch pleated filter. And I think we all gather that. There's a reason that you can't go down to your local hardware store and buy a furnace brand 1-inch pleated filter. They're just not made for it. They're made for the fiberglass filters. If somebody needs something a little bit better than the fiberglass filter, there are alternatives. You can use the 4-inch pleated filters, right? The 4-inch pleated filters have a lot more surface area, and so there's a lot less restriction, but they do also catch more. So oftentimes these 60 days that they tell you that you can leave that thing in there, or even the 90 days on some of them that you can leave them in there, that's way too long. They get too stopped up and restricted by the time that time passes. So you're really still looking at about a month if you're going to put in those 4-inch filters. They're better filters, but only if you use them the way that they're designed to be used. Okay, so that's one of your things that you can change. Second thing you can change, what about your takeoffs? We have the furnace, then we have the coil, and then above the coil we have the plenum, and off the plenum we have the takeoffs. Okay, so we've got our trunk line. How does that trunk line connect to that plenum? Well, if it's a straight collar, simply taking the straight collar off and making that an offset collar or a transitional collar of some sort will help. That 90-degree angle, air doesn't like to take a 90-degree angle. So the more you can ease that angle, the better off you'll be resistance-wise with your ductwork. Now there's all kinds of ways you can look at this. Flex duct is flex duct. Yeah, I think oftentimes we don't use it the way it was designed to be used, and people say, well, how was it designed to be used? And that's up for debate as well. Okay, clearly the picture in the upper left, the picture in the upper right, picture in the lower right, those are easy to look at and recognize, well, that's not the way it was designed. I mean, for goodness sakes, when you look at the upper left there, it looks like somebody bought, a 25-foot run of flex duct, needed to go about 3 foot and decided, I'm using it all, I bought it all. And that's not a great way to look at it. This stuff is designed to be used while stretched straight and braced up every couple of feet. Okay, with a 1-inch strap if you're following code. So could it be laid across the joist like you've got in there? Absolutely it can. Again, as long as it's stretched straight and it's running straight. Any curves, bends, droops, any of that stuff affects the way that flex duct runs. Okay, now the one in the lower left, I particularly didn't mention that one because it looks good. To the eyes, that's pleasing. But it also has two clear 90-degree angles that you can see. One at the top, one towards the bottom. Okay, that is going to really be a hindrance to that airflow. Okay, now when it comes to flex duct, most people would say it's designed to go in areas that are otherwise difficult or impossible to run traditional ductwork through, and I wouldn't disagree with that. However, you've got to use some common clarity on this. Okay, oftentimes ductwork could be run through there. It's just not as easy. Okay, but it is better for the system. It's better for the customer if you run traditional hard duct. There are some areas where flex duct is far more valuable to run, such as areas that have to be insulated or have to be noise proofed. Those areas, it's great to have flex duct in because it's going to inherently be better insulated, and it's going to curb any noise that's going to come from the equipment. Okay, some people use it as a noise dampener just to connect two pieces of rigid duct. So a commercial application, you've got a piece of duct that comes off the trunk line, and then you've got a piece of duct that goes down to where the 2x2 grid is in the ceiling. Oftentimes, between here and here, they'll put a piece of flex duct in there to keep any vibrations from happening in that office area. Genius. That's a great way to look at it. Okay, when it comes to flex duct, just know how it's supposed to be run, know your lengths. There's ductulators out there, and there's specific ones by the manufacturers of flex duct that will tell you how long these things can be run and what kind of CFM you can expect out of it if it's run properly. The blower performance chart. We're going to break this down and make it about as easy as it can be. We don't use this for a whole lot. You see this blue line that's on there, which is oftentimes how the actual fan curve for a particular motor is plotted on a chart like this. It's plotted by taking the resistance versus the CFM, making those meet on the chart and plotting a line. And then you, of course, you make your little graph and it all goes about its merry way and means very little to a lot of people. Okay? However, in looking at this graph and keeping it very simple, on the left-hand side, you have what's called static or resistance in the ductwork. Traditionally, most manufacturers, residentially speaking, don't want you to go above 0.5 inches of static. Some of the efficiency tests allow you to go to 0.8 on a multi-speed blower and up to 1 inch of static on a variable speed blower. Manufacturers oftentimes don't agree with that, so you have a conflict there from efficiency verification programs and manufacturers sometimes. But okay, that's besides the point. So on the left-hand side, we've got resistance in the ductwork. Across the bottom, we've got CFM, or how fast that blower is moving the air, right? Cubic feet per minute of air. So how do we look at this? Okay, this is how we would be measuring the resistance in our furnace. Okay, we put our static measurement in before the blower, so into the blower cabinet. We put a second one in below the coil, maybe into that heating area in the back of the cabinet. Okay, we add those measurements together and we get a certain value. Okay, and then that value is going to be plotted on this chart, taken over to a blower performance chart, and measured with the manufacturer's values. And we'll get to that here in a second. Okay, so look, if you took that blower out of a furnace and had it out in the middle of the floor, and there was nothing pushing back on it, making it difficult for that blower to sit there and circulate. Very, very little resistance. Okay, let's say zero resistance. That's going to be the fastest that motor will ever spin, right? There's no resistance. Equally as bad on the motor, it'll burn itself out freewheeling. However, you get my point. Zero resistance equals the highest amount of CFM. Let's look the other way. People love to have the best filter that they can possibly get. And it's no secret that the more restrictive the filter, the slower the airflow goes. Well, how does that happen? Well, look at this chart. Look where that blue line crosses up there by the 1 inch of static, okay? Between 0.9 and 1 inch of static. Let's say it's 1 inch of static. That's the maximum amount that we're allowed to pull. What is the CFM at that plot mark? The CFM? 0. So at the highest amount of resistance, you have 0 amount of air moving. Picture that as being the most efficient filter you could possibly put in there. A piece of wood. Right? Everybody's got breathing problems. We certainly don't want allergens to get out in the house. Let's put a piece of wood in there to catch everything. But the problem is there's nothing moving through it anymore. The closer the customer or you at your own home get to a piece of wood as your filter, the less airflow you will have. The less airflow you have, the more likely you are to slug your compressor with liquid refrigerant, burn it out quicker. It'll decrease the load and the efficiency of that compressor. Okay, in addition to that, you will overheat the heat exchanger. You'll be moving less air than you should, so overheating the heat exchanger is going to lessen the lifespan of that heat exchanger, for one. And then because the heating speed traditionally is a fairly low speed, slowing that down at all is going to cause hot and cold pockets in the home, more so than what it normally would be. So those things make a difference. The closer you get to a piece of wood, the worse off you are with a filter. There's a reason you can't go down to your hardware store and buy a Carrier 1 inch pleated filter that looks just like the 3M purple filter. Right? You just can't buy those because they're not down there. They weren't designed to be in these pieces of equipment. Now, we use them in the pieces of equipment. because they catch the allergens and the dust mites and all that kind of stuff that's flowing through there. And we figure, well, it's running anyway. We might as well filter the air. They weren't designed to filter the air. They were designed to heat and cool the air. Originally, just heat only the air. Okay, so keep that in mind when you're dealing with the customer. I'm not saying that you should put it so abrasively to the customer. You have to figure out a tactful way to put that to them because they spend a lot of money on those filters. Okay? Better efficiency on the filter also means more money that they've spent. So it really requires a delicate balance of informing the customer and making this equipment work the way that it should. Now here is our performance curve. This is out of the manufacturer's installation guidelines. So what this is used for, you take your static measurement, okay, before the blower and after the blower, you add those numbers together. And over to the left, it tells you what model of furnace you've got. Say this particular one is out of one of the Goodman manuals. Okay, so over to the left, we've got the different models of equipment that this blower performance chart fits. Figure out which one you've got. Look at your actual fan, your blower down in the blower compartment. See what speed that your furnace is running at when you took the measurement. Okay, which give the way you figure out the speed is you figure out what color is the wire. Go over to the wiring diagram, find the blower, and the blower will match up what color wire you have with what speed that is. Now, traditionally, low speed is always red, and high speed is always black. And then you got the fuzzy ones in the middle, like your orange and blue and such. Those are the ones that are a little bit more difficult to keep straight. Okay, so you've taken your resistance measurement. Okay, let's say that we've gotten 0.5, 0.6, 0.7, 0.8, pick one. It doesn't make any difference. We've got medium speed on the GMH 95 0453BX from this chart. Medium speed, you follow that across. Let's say we've got 0.5 inches of static. Medium, following across to the 0.5 inches of static gives us 1,012 CFM. Okay, that's all there is to it. That tells me what kind of CFM I have. Now what does that even matter? Well, if I've got a certain size of air conditioner, I know what that size is because the increments run in 12,000 BTU increments, right? So we've got a 12,000 BTU furnace would be a 1 ton. 24,000 BTU would be 2 ton air conditioning wise. We're looking at 400 CFM per ton, so a 2 ton unit would require 800 CFM. If we were on medium speed here at 0.5 inches of static and we've got 1,012 CFM and a 2 ton unit, we've got too much airflow. We got to slow it down. So we then would slow it down by putting on a slower fan speed, retesting it, and making sure that that's within the framework of what we're looking for. That's how you set up a blower. Is it painful? Not really. The first time, maybe so. But it's once. You set it up one time for the 18 to 20 year life of that air conditioning system. What does the customer even get from that? Are they going to know that you've changed the blower speed 200 CFM? No, they're never going to know. Sorry, you're not going to get a medal in the mail that says you've set the blower up properly. But what you will get is you'll get an air conditioning system that now is set up right on the fan speed. So now you're able to take your temperature drop, which is the temperature coming in the blower compartment versus the cooler temperature coming out, blowing out throughout the rest of the house. You take your temperature drop. If your temperature drop is between 18 and 23 degrees, you know that your refrigerant's right. Right? So you're not going to be adding or removing refrigerant trying to make your temperature drop across that coil be what it should be. If you've got too much or too little airspeed, that's exactly what happens. And although you might get a decent temperature drop, it's never going to fit the capacity that it was designed for, and it's never going to dehumidify right because you've altered the amount of refrigerant that was designed to run in that equipment. So you have to set up the blower speed right the first time. Now, on the furnace, it's a little bit different, right? Setting up the blower speed on the furnace, instead of doing a CFM value, you're then going to get it set right for the BTU value, and then you're going to increase or decrease the blower speed to get you around that 50-degree temperature rise. So if you're setting your blower speed up according to pressure, the 3.5 inches of water column is fairly common across the board. If you set it up for 3.5 inches and that's what your company does, you make sure that that's right. Then you check your temperature rise across that system, right? From the return air to the supply air. If that's around 50 degrees, you're good to go. If it's too low, if it's close to, let's say it's 40 degrees, well, then you might slow a fan speed down. You're not going off of CFM, but you are slowing a fan speed down in order to allow more heat to build up in that heat chamber to get you closer to that 50-degree temperature rise. Okay, now how would you take that measurement? Let's look at that real quick. Here's just an example of a manometer. Checking the airflow and the ductwork. This is really what we're checking. We're checking static. Static is very, very simple. Some guys will just go this far. Right here we've got air moving through the ductwork. They'll put a hole in that edge of the ductwork and they'll just stick their manometer up to that hole. As long as there isn't insulation on the other side that could be blocking that hole, they should get a good static reading, because the measurement is the measurement that's pushing out on the ductwork, not that's running along the inside of the ductwork. Okay, some will actually stick a 1/4-inch piece of tube in there, maybe a static pressure tip in there to get that measurement. Okay, now this measurement right here would be your velocity pressure, and this is different. Right? I don't traditionally use this because I think that there's better ways to get this measurement, but I did want you to see the difference between just checking the resistance in the duct, or not the resistance, but the static in the ductwork, which is a fancy word for resistance, and checking the actual air speed. And this doesn't give you your end value for the air speed anyway. So if you look at it, you've got one tube that's facing towards the airflow. You got the other tube that's facing perpendicular to the airflow. And in looking at that, those are going to offset each other. They're going to give you a value that you would plug into an equation. Now, this is what's called a pitot tube. A pitot tube is a simple way to hook up your high and low sides of your two-port manometer to a system and put it inside of the ductwork and get that measurement of velocity pressure. If you're going to do that, though, you're going to have to plug it into an equation, and nobody likes that. Okay, here's an equation. CFM equals the velocity in feet per minute. You have to do a calculation just to figure all that out. Velocity equals the square root of the velocity pressure that you measured times 4,005. Multiply that times the area of the duct, right? Length times width of the duct on square duct anyway. The area formula for round duct is going to be a little different, right? Pi r squared, 3.14 times the radius of the duct. So 3.14 times, if it's a 6-inch round duct, the radius is going to be half of that. So it's going to be 3 inches, and it's pi r squared. So it's going to be the squared value of that. So it would be 3 times 3. So that's a pretty complicated way to get the airflow measurement. I'm not a big fan of that. But the static measurement, absolutely. Okay, back to this blower performance chart. Static measurement's much easier. You take your manometer, you put it in before the blower, after the blower, get your measurement, add those up. You've got a simple ESP or resistance reading. You correlate it to a chart that's very similar to this. Okay, there are other ways. Okay, this particular method, I believe, is probably one of the things that makes today's method so hard to understand, because this method was not great. Okay, your temperature rise method. Now, how do you get temperature rise? If you look at the values we've got here, we've got a thermometer in the supply, we've got a thermometer in the return on this system. Okay, the difference in the two values there, the temperature going in, the temperature coming out, is going to be what we call temperature rise. So you get your temperature rise. In the traditional method, that's the only value you're actually measuring, and I'm not a fan of that. Look at this. Okay, so this is the way we used to teach it. Your CFM value total on the furnace was your input, gas input, times the efficiency. Now, what does that mean? There's no measured value there. That means if we've got a 100,000 BTU furnace and it's 95,000% efficient, we've got 95,000 BTUs on that top measurement. We're assuming everything's perfect. We haven't even checked anything. Okay? And you're going to divide that by the value you get below, which is the temp rise, the only thing that you're actually measuring, times 1.08. Not a great way to do that. You want to make it accurate? Here's what you do. You could actually clock the meter. That's one way to do it. Clocking the meter is not all that difficult, right? You walk around to the side of the house, you find the gas meter. The gas meter's got 5 dials on it-ish. One of those says half-foot dial. Now, what does that actually mean? Well, 1 cubic foot is equal to 1,000 BTUs. Okay, so we're using a half, so that would be 500. So you count how many seconds it takes for the half-foot dial to go around, and they tell you do it 2, 3, 5 times, whatever. You let it go around more than once, divide by the amount of times you go around. Okay, so if I went around 3 times, I'm taking an average, so I'm dividing it by 3. So if it went around 3 times, took 90 seconds, divide by 3, it took me 30 seconds. That's your example I'm coming up with. Okay, but that's not great because we need to figure out the BTUs per hour. So how many times would that little dial go around in an hour? Okay, so we've got to figure out how many seconds are in an hour to put it into a value that we can actually use in a formula. Well, there's 3,600 seconds in an hour. We divide that by the amount of seconds per the one revolution we said was 30. So 3,600 divided by 30 would be our example. And then we multiply what that value is times 500, and that gives us our BTUs. Right? So that's a much more accurate way to do it. We're actually measuring something. If the BTU value comes up much less or much more than what the manufacturer's tag says it should be, then guess what? You alter it. You increase or decrease the gas pressure at the gas valve on the manifold side so that it's fired properly. When people talk about making sure a furnace is fired properly, that's what they're talking about. So here, the CFM equals the gas meter, or the clocking of the gas meter. So that gives us our top BTU value there instead of assuming stuff. And then you're going to divide that by the same stuff we had before, which was the temp rise times the 1.08. There are other ways for other pieces of equipment. We've got oil furnaces out there. Okay, it gets a little more complicated when figuring out that value. Okay, figuring out the airflow on an oil furnace. You got to figure out the nozzle rating. Multiply that times the oil heating value. Well, the oil heating value has to come from the supplier. So you have to call them and get that. So CFM is going to equal your furnace input times the efficiency, and the furnace input equals your nozzle rating times the oil heating value. So there's one extra calculation you have to do in that top section there in order to actually get your measurement. And getting into the electric side of things, it's even more involved. In my opinion, also more accurate. CFM on electric heat. Okay, the actual formula is heater capacity in BTUs divided by the temp rise times the constant value we're using of 1.08. Okay, so how do you figure out the heating capacity? Well, heating capacity equals the amount of kWs times 3413. Well, how do you figure out how many kWs? Well, you could read on the manufacturer specs, but that doesn't mean that that's the kW that it's putting out in the equipment. You have to measure it. So it's measured volts times measured amps divided by 1,000, right? Measured volts times measured amps divided by 1,000. So your watts divided by 1,000. So you figure that out, plug it into the calculation before, which was a kW times 3413. Figure that out, plug it into the original calculation, that gives you your value. So back to EER, where we started this entire conversation. EER requires one more step than what most evaluation forms require. They don't necessarily take the same value in the BTU, or the cooling capacity of the equipment, as they do in the EER. So what's the difference between SEER and EER? Okay, the difference is when it comes to SEER, that is the value that the manufacturer gets before there's ever any installation out in the field, right? This is the best possible scenario. I always use the example of a Camaro in the factory on an air dyne under the perfect temperature and non-wind situations. That's where they get their gas, their gallons per mile, or their miles per gallon rating on those cars. It's never going to get that for you probably out in the real world. And the same thing with SEER on a piece of equipment. EER is a timestamp of what happens when dum-dum gets involved. When I put that in and it's on the side of your house, now how good's it run? They want me to measure that. Okay, and there are certain values I've got to do. We went through CFM already. And we talked about external static pressure. Well, here's your before and after the coil. You can clearly see there's a coil, the triangle, sitting on top of the furnace. Okay, the rectangle sitting below that with a little dotted line in there, that's your furnace. You've got a top compartment and a bottom compartment. This example, we've got a bottom compartment that has a blower in there. Okay, so we've put a penetration in the back of the blower compartment and in the back of the heating area. And we're taking those measurements with a static pressure tip. And those are very, very inexpensive, by the way. A static pressure tip probably going to cost you maybe 10 bucks. Okay, you can use one, and you can go bottom first, and then do top next, and then add those values together. And that gives you your total external static pressure. And people get confused. Why are we not doing that after the coil? Why are we doing it before the coil? Well, because we need to know what the resistance is that coil puts on the system, because that blower is pushing through it. We're trying to set that blower up to work properly with that coil, and the only way that we can do that is make sure that the coil is in the measurement, okay, as we're doing it. Same thing with the filter on the other side. So those are your penetration points for checking your external static pressure. Your EER verification, okay, you also have to get your enthalpy. Here's an enthalpy chart. Okay, this enthalpy chart I told you was pretty straightforward, fairly simple. Right? The enthalpy chart tells you got to have the wet bulb temperature. The wet bulb's on the left-hand side here, and the enthalpy sits right next to it. Right? What's your heat absorption that we're talking about here? When you're looking at your heat pump verification form, these are your basic understandings that you've got to have. How do I check the airflow? How do I check my air temperature? Right? I've got my supply temperature, my return temperature, and then I convert that over into enthalpy with a chart. Then I do a calculation that gives me the BTU value, and then at the very end of that, I've taken the watts, which is your next step, which is your volts times your amps, measured volts at the condensing unit, times measured amps at the condensing unit, both while running. You take your BTUs divided by watts. That gives you the EER value. Right? Here's your BTU value. Your watts, very simple measurement to get. It's at the condensing unit. You get your volts while it's running. You get your amps while it's running. Volts times amps gives you watts. You clue that back into the formula with the BTU value. The BTU divided by watts gives you the EER, or the actual efficiency of how it's running right now, which is going to be much different than the SEER value. Remember, okay, you've got to keep in mind the SEER rating is your best possible performance it's ever going to get. Your EER is how it's actually working right now. If that was the value that a state or local entity was using and making sure that your install lived up to their expectations, what does that force you to do? Well, it depends. Some of these efficiency tests allow you to enter the stuff in on a computer program. And if it doesn't work out, you can go back in there and you can add a different number here, add a different number there until it works, and then you can submit it. While other efficiency programs say, no, we're not going to do that. You write it all down on a form. Once you send the form in, we're not going to tell you what the EER value should be or what we're going to consider good. Okay, what does that do for you as a service technician? It requires you to do everything under the best possible circumstances to make sure the customer gets the value for the installation you just put in, and to make sure that you save face with the customer because it's working the way that it should, because customer's going to know if it passes the efficiency test or not. So what does that mean? What's best possible scenario? Well, we know most efficiency tests won't pass if they're done below 69 degrees. So 69 degrees is usually your cutoff. We know the efficiency test isn't going to pass if we've got too restrictive of a filter or too small or restrictive of ductwork. So if we haven't planned to alter those things or educate the customer on what to use, chances are it's not going to pass. We know that if it doesn't run long enough to get a wet coil, chances are it's not going to pass because it's not under the optimal conditions that most of these measurements require to be taken in the air conditioning mode. If we've got a system that's been sitting there for a long time, now it's got cottonwood and all that kind of stuff on there, well, we know it's probably not going to pass because it's not going to pass the efficiency side of things when we take our wattage reading on that. If we've not set up the blower performance correctly and we had to overcharge or undercharge the system, again, that affects the wattage. Not going to pass the efficiency test. Not going to pass the dehumidification test or the enthalpy test either. Okay, so a lot of things are taken into consideration when it comes to efficiency. It's not about checking on everybody. It's about proving that what we're doing makes a difference. It's about proving to the customer we are who we say we are. We're the professionals that we've always been, and here's why. These are things that, yeah, if you had somebody else do it, they might do these things, but they might not. And they might not even understand why I did them or how to do them themselves. That's what sets some organizations apart from other organizations. It's the extra knowledge that allows them to go one step further in customer verification and also setting up these pieces of equipment. Remember, EER is different from SEER rating. SEER rating is done in a factory before it ever gets on the side of my house. EER is done on the side of my house in real time as a timestamp and a proof as to how good I've done my job on an air conditioning system. You get the EER by figuring out the BTU value, divide that by the measured watts. Okay, now that we've talked about the different forms, different methods for getting your measurements, this is my simplistic approach. This is the form that I would use. There's only a couple of steps to it, right? And that's what it's all about. Just something that makes it quick and easy for me to check to make sure that what I've done is right. That's it. I don't need somebody looking over my shoulder or somebody telling me that I've done this or that or the other wrong. I don't need to come back in a month because I gave them a taillight warranty and I did a rickety install. So look at this thing. When it comes to your air conditioning side, your first step is to check your ESP, your resistance in the ductwork. We talked about that already. It's in the blower cabinet and then before the coil, right? After the filter, before the coil. use your static pressure tip, get a resistance measurement from each of those locations, add them together. It's got to be 0.8 or less on the multi-speed blowers, 1 inch of static or less on a variable speed blower. Then enter in your CFMs on the far right. Now, in the B section, it says run at least 10 minutes. Really what we're looking for here is a wet coil. Okay, so if it's already been running and you've got a wet coil, you got condensate coming out of the drain line, you know that you're in the ballpark of what you're supposed to be doing. Okay, so step 1 here in B tells you to get your measured watts. What does that mean? Your measured volts at the condensing unit, your measured watts while the condensing unit is running. Okay, volts times amps is going to give you your watts. You plot that in there. Step number 2, your return wet bulb temperature and your supply wet bulb temperature. Plug both of those temperatures in. That's a special meter that gets your wet bulb reading. What's the difference between wet bulb and a traditional dry bulb thermometer other than 20 bucks? Your biggest difference is wet bulb thermometers take into consideration the humidity as well. And that's a new part of what we're doing these days as well. We don't just want to cool the air. We want to make sure that we're dehumidifying it as well. You ever been outside on a super humid day? It might be in the 80s, but it feels close to 100. So if we can dehumidify as well as cool the air, it'll feel much more comfortable in the customer's house. Okay, so get your wet bulb temperatures, return and supply. Take that over to the enthalpy chart, which you can get off an app or you can download off the internet, and plug in your enthalpy readings for those wet bulb temperatures. Subtract the enthalpy difference. Okay, your supply and return that you just entered in with the enthalpies right next to it. Take those two enthalpies, subtract them, plug that into step 3. Steps 4 and 5, simple calculation. 4.5 is a constant that we're using for this calculation. So 4.5 times the CFM that you got in A1 times the enthalpy difference that you got in B3 equals your BTU value. Now, in step 5, you take the BTU value, divide that by the watts that you got in B1. That's going to give you your EER, which is a timestamp of how efficiently this piece of equipment is operating now that you're actually done with your installation. So effectively, we know it was a high SEER rating when you bought it, but what happened when Dum Dum got involved? That's what we figured out.